Hey everyone, and welcome to this explainer. I'm absolutely thrilled you're here today because we are going to unpack something truly fascinating. We're looking at the incredible evolution of how humans map space and time. I mean, think about it. From ancient astronomy in India all the way to the global coordinate systems powering the GPS on your smartphone right now, our understanding of the globe has gone through a massive evolution. So if you love seeing how the pieces of human history, science, and geography fit perfectly together, you are in the exact right place. But before we get bogged down in all the grids and the math, we really need to take a step back and ask a deep, fundamental question. How do we actually locate ourselves in an ever-changing world? This is really the heart of social science. It isn't just about memorizing state capitals or historical dates. It's about understanding our shared human society. We live in an age of brilliant technological possibilities, for sure, but we're also facing massive challenges like environmental stress and social conflicts. To solve humanity's problems and protect this beautiful Earth we all share, we first have to thoroughly understand the diverse canvas we live on. So, to do exactly that, here is our multidisciplinary roadmap for today. Number 1, our shared human society. Number 2, the basics of map reading. 3, the global coordinate system. 4, Ujjaini to modern Greenwich. And finally, number 5, the science of time zones. All right, kicking things off with Section 1, our shared human society. Okay, let's dive into this. To solve our shared challenges, we absolutely must understand the geographical world around us. Geography is foundational. Things like oceans, mountains, and rivers, they don't just exist in the background. They have actively shaped entire civilizations throughout history. Listen to this quote. "The globe of the Earth stands in space and is spherical." Now, that wasn't said by a modern astronaut looking out a spaceship window. That was stated by the brilliant ancient Indian scholar Aryabhata around the year 500 CE. Centuries before we had satellite imagery, ancient Indian astronomical traditions had already laid down this foundational understanding that we live on a sphere floating in space. And honestly, this early knowledge is absolutely critical to the history of how we map our world today. Moving right along to Section 2, the basics of map reading and how we shrink the world. Once you accept that the Earth is a sphere, you hit a very practical problem. How on earth do you represent a giant ball on a flat piece of paper without completely distorting it? Think about it. It's like trying to peel an orange in 3 or 4 large pieces and then flatten that skin onto a table. You literally can't do it without tearing or warping the edges. So, since maps are flat representations viewed from above, making a massive place fit on a tiny piece of paper requires a map scale. A scale is basically a ratio. It's the magic trick that shrinks massive real-world distances down into a readable, navigable format. So, how do we actually use this in real life? It's basically a 3-step cheat code for practical navigation. Step 1, check your map's scale in the legend. For example, it might say 1 centimeter equals 500 meters. Step 2, take a physical ruler and measure the space between 2 points on the map. Step 3, just multiply that ruler measurement by the scale. So if your ruler says 2 centimeters, boom, you know your real-world destination is exactly 1,000 meters away. It's incredibly empowering math that lets you navigate your local environment with total confidence. Now, aside from scale, mapping relies on 2 other essentials: direction and symbols. We use the classic cardinal directions, north, south, east, west, along with intermediate ones like northeast or southwest, just to orient ourselves. And because we obviously can't draw highly detailed real-world buildings on a tiny map, we use symbols. For instance, the Survey of India has fixed standard symbols for things like rivers, broad-gauge railway lines, post offices, and temples. This lets a single piece of paper communicate a ton of complex information in a very limited space. Okay, let's zoom out. Section 3, the global coordinate system. We've looked at local street maps, but how do we locate a specific city on this massive spherical globe? We need a grid. Now, what's really interesting here is comparing this to something familiar, like a chessboard. Advanced chess players track their moves using a grid of letters from A to H and numbers from 1 to 8. So if you open a game by moving your pawn 2 squares forward, you easily record that as D4. Well, the Earth's global coordinate system uses the exact same logic. Instead of simple letters and numbers, we use latitudes and longitudes to give every single spot on Earth a precise 2-part address. Let's define that first coordinate. Latitude. If you look at a globe, the North Pole and South Pole are fixed points, right? Halfway between them is a circle called the equator, sitting right at 0 degrees. Latitudes are imaginary parallel lines that measure your distance north or south from the equator, going all the way up to 90 degrees at the poles. But here is the really fascinating part. These horizontal slices also dictate global climates. The equator is hot and torrid, but as your latitude increases toward the poles, the climate shifts to temperate and eventually to completely frigid. Our second coordinate is longitude. Imagine drawing the absolute shortest possible line connecting the North Pole straight down to the South Pole. These vertical half circles are called meridians of longitude. They measure our distance east or west from a starting point. And as we're going to see very shortly, these vertical lines are the absolute key to calculating global time. Which perfectly tees up Section 4, Ujjaini to modern Greenwich, and the search for a prime meridian. So if latitudes start naturally at the equator, where do longitudes start? Fixing a 0-degree longitude line, a prime meridian, is fundamentally just a human decision. Fast forward to 1884, and an international agreement established the prime meridian at Greenwich, London. But this is where the history gets really cool. Many centuries before Europe standardized this, India had its own vibrant prime meridian. Ancient Indian astronomers, folks like Varahamihira, working around 1500 years ago, understood global coordinates perfectly and established their very own zero meridian for their calculations. They called it the Madhya Rekha, which translates to the middle line. This ancient Indian prime meridian passed directly through Ujjaini, which we know today as Ujjain. It was prioritized by astronomers because of its precise geographical position, often noted as intersecting the Tropic of Cancer. Now, establishing this ancient standard required incredibly accurate local timekeeping. So while today we universally use the 1884 Greenwich Meridian as our 0-degree standard, it's absolutely vital to recognize how India's rich astronomical heritage pioneered the mapping of global time and space long before modern conventions. And that brings us to the final puzzle piece, Section 5, the science of time zones. We've got our map, our grid, and our prime meridian. Now for the planetary physics behind our daily clocks. Why the number 15? Well, let's do the math real quick. The Earth makes one full 360-degree rotation on its axis every 24 hours. If you divide 360 by 24, you get exactly 15. This brilliantly illustrates that the Earth spins exactly 15 degrees every single hour. Because the Earth rotates from west to east, places to the east see the sun first. So if you travel eastward from the prime meridian, you add time, roughly 1 hour for every 15 degrees of longitude. If you go west, you subtract time. Now, if everyone used strict local solar time, it would be absolute chaos for a country to function. Imagine trying to run a national train schedule where every single town is a few minutes off. That's exactly why countries adopt a standard time based on a central meridian. For example, Indian Standard Time, or IST, coordinates the entire country by staying exactly 5.5 hours ahead of Greenwich Mean Time. But what happens when a country is just ridiculously geographically wide? India uses one time zone, which works great. But massive countries literally cannot do this without throwing their clocks completely out of sync with the sun. The USA has 6 time zones. And Russia? Russia spans such a massive stretch of longitudes that it requires 11 standard time zones. If you travel from the east coast of Russia to the west, you'll literally have to readjust your watch 10 times just to keep up with the local time zones. No way, right? Okay, ready for a real mind bender? If the prime meridian is at 0 degrees, what happens on the exact opposite side of the globe at the 180-degree longitude line? This is known as the international date line. So what actually happens when you cross it? This is where geography basically allows for real-life time travel. If you're on a ship crossing the international date line traveling east, you literally subtract a day from your calendar. You go back from Monday to Sunday. And if you cross it traveling west, you jump forward and add a day. The line zigzags just a little bit to avoid cutting countries in half, but it is the definitive boundary where one day ends and the next one officially begins. And that brings us full circle. We've explored how ancient scholars in Ujjaini look to the stars, how mapmakers shrink the world onto paper, and how the spinning of our planet creates the time zones we live by today. But remember our very first question at the start of this explainer? Geography isn't just about maps and clocks. It is the absolute foundation of social science. It shows us that despite our different time zones and climates, we are all living on the exact same intricate spinning grid. So I leave you with this. As we continue to map our beautiful, diverse differences, how can we use our shared understanding of this Earth to better protect the only home humanity has? Thank you so much for joining me on this explainer, and as always, keep exploring.